G'day chemistry students. In this video we're looking at dot point 5.4.4. The focus of the video is to start looking at how we can do calculations for equilibria, in particular solution equilibria. We're going to be looking at how to calculate KSP, which is the K value, the equilibrium constant for solution equilibria, as well as also being able to calculate ion concentration and from that being able to determine solubility. Let's get into it. First off, let's have a quick look over at what solubility products are. We label them KSP. These products represent the concentration of ions that you have when a solution is at a point of saturation, meaning that the solution cannot hold any more of these ions. We end up having a reaction equation, an equilibria that looks like this. You have the solid on the reactant side and the aqueous components on the product side, and all it's showing is the dissociation in correct ratios. The solubility product is then just the product of the concentration of all of those products that we get at the end, those ions, the cation and the anion. And you'll notice that it follows the same kind of rules that we looked at when we're doing equilibrium constants for any other equilibrium process. You'll notice in particular that there is no denominator. That is because there is no concentration for the solid itself, so it is not a part of our K expressions. When we calculate KSP, what we need to be doing is following a very similar set of steps that we would do to calculate any K value. We find the balanced chemical equation, we write up the equilibrium expression. In this case, we'd be writing up a solubility product. We would then identify concentrations that are in the question or find them out, calculate them for both of the ions that are present when we're at that point of saturation or that point of equilibrium. And then we substitute all the concentrations in and get our KSP value at the end. There's a practice question that will come after the next couple of slides. So these are some KSP values that you will find in your data sheet. This isn't for every single ionic substance that could be used in a HSC style question. In particular, it's a bunch of insoluble salts or salts with very, very, very low solubility. These can be used for all sorts of problem solving questions in an exam or HSC conditions. If you are required to use a KSP value which is not listed here, it will be included in any question that you are given. We can also use these KSP values to calculate ion concentration. So that's knowing that you have a substance, it's in solution, it's completely saturated. You can then use the KSP value that's been determined previously to then find what the concentration will of the ions will be. So to do that, again, like normal, we write up the balanced chemical equation and equilibrium expression or a solubility product. From there, our unknowns we can label as X. When we're trying to name an unknown ion as X and its concentration, we usually try to go for the one with the ratio of 1 in its empirical formula. For example, down here for magnesium chloride, I chose the concentration of magnesium to be X, not the concentration of chlorine. This makes the rest of the question a little bit more easier to process mathematically. If you do have other unknown concentrations, you can also write them down as well in terms of X. So depending on their stoichiometry or empirical formula or anything like that, you might get X or 2X, 3X, depending on what those ratios are. What we can then do is put our X values into the solubility product, rearrange the equation for X, substitute any known concentrations and solve. Very, very, very similar to the techniques that we're doing to find the concentrations of unknown substances for our general KEQ values. Using that information, we can also find the solubility from KSP. So I've just put in an extra step for this. Once you know what the ion concentrations are, you can use your stoichiometry, your ratios, to find out what the solubility of the solution would be overall. So for example, in the scenario that I outlined up here, what we can do is say, well, the concentration of the whole solution will be the same as the concentration of the magnesium ions. That is because they are directly in a 1-to-1 ratio. Got a couple of practice questions to quickly go over, so let's get over to those. Our first practice question for this video reads as follows. The solubility of zinc hydroxide is 0.001 grams per 100 grams of water at 298 degrees Kelvin. We're being asked to calculate the solubility product, or the KSP, for zinc hydroxide. Now, the first thing that we need to do is identify the balanced chemical equation. So we're looking at this substance here, zinc hydroxide. The best version of this question would say that it's zinc 2 hydroxide. We generally assume that zinc is 2 unless told otherwise. If that's the case, then solid zinc hydroxide is going to exist in a 2-to-1 ratio. The zinc has a charge of +2, the hydroxide has a charge of -1. That gives us our zinc hydroxide solid. And we know that we're talking about solubility, so we're looking at the process of dissociation, of dissolving. So that is going to lead to the formation of zinc 2 plus ions and 2 lots of hydroxide ions. Once that's done, we can then write up an equilibrium expression. That is KSP is going to be equal to our product of products. So our zinc ions and our hydroxide ions, which I'm going to square, noting that we do not include our solid. It doesn't have a concentration, so we won't say that for any of our solubility products. That's our KSP value done. What we then need to do is determine the concentrations of our ions when it's at equilibrium, and then put all of that in that steps 3 and 4. So what I'm going to be doing next is determining in this question the concentrations of both of those ions, and that's going to be based on this information here, what the solubility is up in the question. So what we know is that zinc hydroxide will dissolve to the point where there is 0.001 grams in 100 grams of water. In other words, that's 0.01 grams per litre of water. And that gets us a really nice starting point. Now, when we're using our concentrations, we need to be using molar values. So to do that, I'm going to determine from this mass in a litre how many moles that is. So N is equal to M over MM. That's 0.01 divided by the molar mass of zinc hydroxide, which you can just calculate using molar masses from the periodic table. That comes to 99.4 grams, which is 1.01 times 10 to the -4 moles. And we can apply that to the concentration that we had up there. So if 1.01 grams is dissolved into a litre, that's equivalent to 1.01 times 10 to the -4 moles in a litre of solution. Once we know the concentrations, we can then start to determine the concentration of the individual ions. So the concentration of zinc ions by itself is equal to the concentration of zinc hydroxide. So that's going to be exactly the same. 1.01 times 10 to the -4 moles per litre. And the concentration of hydroxide is going to be double the concentration of zinc hydroxide. And that's got to do with our empirical formula and our ratios. So that's going to be equal to 2.02 times 10 to the -4 moles per litre. What we need to do right at the end is then just substitute those concentrations at equilibrium. So what we're saying here is if we form a saturated solution of zinc hydroxide, we're going to have zinc ions in the concentration of 1.01 times 10 to the -4 and a concentration of hydroxide ions at 2.02 times 10 to the -4. So the KSP value, is as it is up here. So that's 1.01 times 10 to the -4 times 2.02 times 10 to the -4. And all of that is squared based on our formula above. When all of that is entered into a calculator, what you should get is 4.12 times 10 to the negative 12, and that is our KSP value for zinc hydroxide. Now, in this second question, we're going to be calculating ion concentration from KSP given in the question. And I'm going to take that one step further and use those ionic concentrations to then also calculate solubility, which essentially means adding on step 5 at the end. So the question doesn't ask for the solubility, but I'm going to add that on to the expectations to the question anyway. So our question reads, the KSP for calcium iodate, CaIO3, and there's 2 of those iodate ions, is 6.47 times 10 to the negative 6 at 25 degrees Celsius. We're being asked to calculate the concentrations of the calcium ions and the iodate ions if the solution is saturated. So what we need to do first, similar to what we did for our previous questions, is first identify the balanced chemical equation. So I'm going to write that out first. So we have our calcium iodate. And we know that if we're looking at saturated solutions and solubility, what we're trying to do is split that up into its aqueous ions. Also going to note that this is solid. So we have calcium 2+, and that's aqueous. And we have our iodate ions. We have 2 of them. And that's aqueous as well. And just to note, the reason why I know that calcium is 2+ and iodate is negative comes down to the ratios in our empirical formula over here. Next thing that we need to do is write down our equilibrium expression, our solubility product. So KSP is going to be equal to the product of our ions, which is our calcium ions, and our iodate ions, IO3 minus. And also note that I am going to square this value due to our ratios in the empirical formula. Now, in this question, what we have been given is the KSP value for calcium iodate. We haven't been given the concentrations of those ions. That's what we're actually being tasked to find. So what we need to do next is do a little bit of work to set our unknown ion concentration as X, and in particular, the bit that has the ratio of 1, which is our calcium, we're going to be labeling as X first. So I'm going to let the concentration of calcium be equal to X. And as a result, because we also need to find the concentration of the iodate, we can say that the concentration of IO3, our iodate ion, is going to be double the concentration of the calcium ion, so 2X. So what I've just done then is write down the value of our other term using our stoichiometry. But what we can do with that afterwards is substitute in the X values into the solubility product. So in other words, KSP we can now say is X times 2X, which is our iodate concentration, all squared. I'm going to do a little bit of quick math before I go any further and just say that that is X times, and remember that we need to use our index rules here. So that's 4x squared, which really is 4x cubed all up when we put it all together. So the next thing that we need to do is rearrange for x. So I'm going to put x on the other side for a bit of simplicity. I'm going to divide KSP by 4 first, and then cube root all of that afterwards. Once we've rearranged for x, we can then substitute in our known concentrations, which we don't have any of, but we can substitute in the KSP there to solve for x. So we've been told at the top the KSP is 6.47 times 10 to the negative 6. I'm going to put all of that in. So the cube root of 6.47 times 10 to the negative 6 all over 4. When we put that into our calculator, we should end up with 1.17 times 10 to the negative 2 should be our x value, which is our concentration of calcium ions. We can take this value and use it to be able to also calculate our iodate concentration, which we know is going to be 2 times our calcium concentration, or 2x, as we noted up above. So that's this one here. So that's going to be 2 times 1.17 times 10 to the negative 2, which should come out as 2.34, or 2.35 if we round up correctly, times 10 to the negative 2, and that's our answer for both of our concentrations. And we can take these values and use them for step 5 up here to be able to determine the solubility of solution. To do that, what we can say is that the concentration of the calcium iodate is equal to the concentration of the calcium ions. That has to do with the ratios in the empirical formula. So we already know that the concentration of a calcium ions is 1.17 times 10 to the negative 2 moles per liter, and that is our solubility. Note as well that we should be putting our units in for our final answers here as well. I'm just going to add that really quickly. And there you go. We have gone through the process of determining the concentration of our ions when we hit that point of saturation. And we have also been able to use those ion concentrations to be able to figure out what the concentration of the salt is at that point of solubility, at that point of saturation. And we've written down our solubility in moles per liter there as well. Thank you very much, everyone. In this next video, what we're going to be doing are some further calculations based on KSP. We're going to be looking at the size of KSP, what that means for different kinds of equilibrium systems, and how we can use a QSP versus KSP style of calculation to make predictions about equilibrium systems as well. But until then, have a good one.